Alright, gang, here we go. This is Chem 2, Unit 2, Chapter 7. Alright, so this is the last chapter in Unit 2. Alright, we're just going to hit the high points on here. So in this video specifically, we're going to talk really briefly about the history of the periodic table. And then we'll also talk about periodic trends. And then in the next video, we'll talk about general properties of some of the areas of the periodic table, etc., so on and so forth. Alright, so development of the periodic table. Okay, so I think this stuff in general, I think is super fascinating. There's this really good book, I've probably mentioned it in class, called The Disappearing Spoon. Alright, totally worth reading. And so not only it kind of goes through the history of the periodic table, how it was, how it was developed, and how the elements were found, and so it goes into the science of how these elements were discovered. But and that's pretty interesting. But I think what's more interesting is all the politicking that goes on in the science world as well, and just kind of how all that came about and all that stuff. It was like a really fun book. Alright, so if you have any passing interest in the history of the periodic table at all, check out The Disappearing Spoon. Alright, Dmitry Mendeleev is the guy that kind of gets the credit most for developing the periodic table as we know it today. Lothar Meyer is, for whatever reason, he's just kind of, even though he did almost the exact same thing at almost the exact same time, kind of gets put on the back burner. Like if you ask people who developed the periodic table if they have anybody to say, they'd say Mendeleev. All right, but so it's kind of interesting that they both came up to it. But anyway, so what they did is they both came along and organized the periodic table based on atomic mass. Now we have the periodic table based on atomic number, but back then they didn't really know about the protons, etc., so they didn't have that to measure it based off. So they'd use the mass of the atoms instead. Not only that, but they get credit for it because they organized it by atomic mass, but then they also put these elements into groups to organize them based on their properties. All right, and so that's what made it periodic, because the properties appeared periodically, so you could actually predict based on their location what their properties would be. But not only that, but they also both had the idea that there would be blank spots in the periodic table, elements that hadn't been discovered yet, and based on those, the blanks, they actually predicted like melting points and boiling points, densities, and reactivities of elements that hadn't been discovered yet. And so that's really what gave them, kind of put them over the edge with like getting the credit for developing the periodic table. All right, this is kind of interesting. I find this kind of thing fascinating. That this tells, based on the color in the periodic table, it shows what years they were discovered. Okay, notice that like 1735 to 1843 was the gold rush of an element discovery. Okay, before that, like, elements weren't really an idea. They were to an extent, but not completely. And then as the John Dalton's ideas and so on and so forth started to take root, like elements started to get discovered a lot more frequently. I also think it's pretty fascinating, like some of the trends that appear. Notice that these pink ones here there are 11 elements that were discovered between 1894 and 1918. So in a 24-year gap here, there were 11 elements, and they're primarily, like, a big chunk of, or a couple of them here, are these noble gases. And so, like, the noble gases, even though they were low atomic masses, or especially neon and argon, arguably, they still took a while to discover compared to many of the other elements. And, if you think about it, like, that makes sense because they're really non-reactive. Okay. Anyway, so Mendeleev, so he organized them based off properties, and then he also predicted missing elements, so on and so forth. So here's some stuff for germanium and silicon that he came up with. I still think Eka would be a cooler name for silicon, but whatever. All right, he based it. So we kind of already talked about this. So he based it off atomic mass. Okay, and because that's the fundamental property they had at the time. And then about 35 years later, Ernest Rutherford came along and discovered the nuclear atom. And then Henry Moseley finally came along and then just determined or he kind of like developed the concept of the atomic number, and did it so experimentally, and then they decided to rearrange the periodic table based on that, and this kind of changed some things because there are certain elements that actually on their average atomic mass is higher than elements that are right next door to it. Let's see. So like for example, cobalt and nickel is like the quintessential example. Lots of people point out about that because cobalt, its average atomic mass is actually heavier than nickel's average atomic mass. All right. So anyway. So then we got periodicity. So this is really where the name the periodic table comes from. All right, it's the repetitive pattern of property of elements based on their atomic number. So this is the idea that as we move across the periodic table, we have this repeating pattern going on. Okay, and so these are the ones that we'll be discussing in this chapter. Okay, so this video we're going to focus on these guys here. Subsequent video we'll focus on this one here. Okay. So first we're going to talk about the fundamental property that leads to many of the trends, and this is the effective nuclear charge. All right, so like in your notes or somewhere, like I just want you to, jot down a periodic table real quick. All right. All right, because we're gonna keep track of our trends as we go through the video. All right, so there's my periodic table. We'll be jumping back to that slide a couple of times. All right, so effective nuclear charge. Now this is the one that you can use to hang your hat on almost all the other periodic trends. Okay, so anytime I ask you to describe why does that periodic trend occur, always think about effective nuclear charge first, because 9 times out of 10, effective nuclear charge is going to be the place you can hang your hat to say, well, this trend happens because the effective nuclear charge is increasing or decreasing, and then what is that, et cetera, right? So that's, that 9 times out of 10, that's the great place, that is the place to start. Okay, so effective nuclear charge, very, very important. In essence, what we're thinking about is the effect that the protons in the nucleus have on the valence electrons. Okay, now you can almost think about the protons in the nucleus, they are defined as positively charged and electrons are defined as negatively charged. You could almost think about these things as magnets. Okay, the protons are positive, the electrons are negative, and they're getting pulled towards each other. Okay, so that's kind of what we're imagining when we think about effective nuclear charge. All right, you might also hear me refer to it as Z effective. All right, so anyway, so with effective nuclear charge, we're thinking about how do these nucleuses, or these protons within the nucleus, affect these valence electrons. All right, now remember, valence electrons are the outermost shell of electrons. Okay, now the nucleus is going to be pulling these electrons towards themselves, right? The protons are positively charged, the electrons are negatively charged, so the electrons are going to be attracted towards the nucleus. That makes sense because they're opposites and opposites attract. But at the same time, there might be core electrons. The vast majority of elements have core electrons, or any element or any electrons that are not valence electrons. Okay, so these core electrons are negatively charged. The valence electrons are negatively charged. So that means because they're both negative, they're going to be repelling each other. So these valence electrons are both being pulled towards the nucleus because the nucleus is positively charged, but also being pushed out away from the nucleus because there's electrons in the way. All right, and so as we go gain or lose protons, our effective nuclear charge is going to lose or gain effectiveness. All right, so this is in general how we calculate it for this class. Now this formula is a fair bit of a sneezing tree. All right, and so take this with a grain of salt. This is a good way to think about it, but there are a fair number of exceptions. It does a good job predicting general trends, but when you get into the nitty-gritty of the trenches, this formula kind of falls apart in some places. All right. So anyway, so Z effective can be found this way. All right. So Z effective, remember capital Z almost always means protons, okay, or the atomic number. So Z effective is equal to Z, which is the number of protons minus S, and those are the shielding electrons, or the screening constant. Okay. So really, you're thinking about the core electrons. Okay, number of core electrons. All right, that's your S values there. Okay, so so generally in our case, you can just take the number of core electrons is equal to the electrons of the number of electrons of the noble gas before it. Okay, gas before. All right. So anyway, so like if you look at this here, as we're going across the periodic table, so it starts with lithium here, okay? Now the red line here, the green line with the triangles, this is using this formula here, all right? So really pay attention to this green line right now with the triangles. So lithium, okay, let's just calculate a few of these so you can kind of get an idea of how it works. So Z effective is equal to Z minus S. Well, lithium has an atomic number of 3. Okay, it's the third element, atomic number of 3, so our Z value is 3, and then our S value is the number of electrons of the noble gas before it. All right, well, the noble gas before lithium is helium, so therefore the number of shielding electrons is 2, so the Z effective for lithium is 1. And notice that the green line is right here, it starts at right here at 1. Let's do beryllium and boron real quick. So beryllium is element number 4, so it's got atomic number 4, and the number of electrons that the noble gas before it has, well, it's still the same, right? Because the helium is still the noble gas that came before it, just like for lithium. So the Z effective for boron is 2, and then you can see as we move up, okay, boron would be 5 minus 2, and we get 3. So you could see as we move left to right across the periodic table, we simply go in integers 1, 2, 3, 4, 5, 6, 7, 8, and when we get the noble gas, then when we restart our row, we jump back down to 1, 2, 3, 4, 5, 6, 7, 8. All right. So generally, our effective nuclear charge increases as we go across a period, and that makes sense, right? Because as we go across our period, our nucleus is going to be more effective at reaching those outermost electrons because there's more protons, but the same number of shielding electrons. All right, so as we go across a period, our Z effective increases. Now, the tricky part is how does it work when we go down a group? Okay, now the Z effective increases slightly as we go down a group. We can't use this formula to predict how it is affected as we go down a group. It doesn't work because the number of valence electrons and the core electrons are going to keep having that same ratio. Look at or the same number, or the same differences, excuse me. So like for example, lithium and sodium. Now lithium's right above sodium on the periodic table. They're in the same group, but according to this formula, the formula we have up here, our Z effective for both of them is equal to 1. All right, so that doesn't quite work. And then we can keep throwing. You notice this green line goes 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. So, it doesn't quite predict what happens as we go down a group. Thank goodness we have other ways of, predicting and calculating and measuring Z effective. And we can actually see based on these lines here that our Z effective is actually slightly higher as we go down the group. Okay, so notice how like the noble gas for fluorine, it's around a 6-ish, for this blue like 5.9 or so, but then for the next noble gas, argon here, it's over 6, probably close to like 6.5 or so. So anyway, so that kind of allows us to get us a better idea. So the two things you need to know is Z effect. You need to know where it comes from. You need to know why it increases as we go across a group. Okay, and you need to know this trend. So let's draw it out real quick. So Z effective, all right, increases as we go across a group, all right, and then it also increases slightly as we go down a group. Oops, sorry, did I say a group? Across a period and down a group, all right? So make note of those. All right, so that's effective nuclear charge. All right, now we're going to move on to atomic radius. Okay, now we're thinking about two things here. There's just general ideas about atomic radius that we want to make sure that we're clear on. All right, bonding atomic radius is equal to half the distance between the two nucleuses that are being bound. All right, so really it's, from so that's the nucleus that's being bound right there, and there's the other one. That distance there divided by 2 gives you your bonding atomic radius. All right, that's defined as your bonding atomic radius. All right, and that's as close as those two can get. Your non-bonding atomic radius is the distance between the nucleus and the outermost shell, or the valence electrons. That's the non-bonding atomic radius. So those are both those values you kind of have to keep in mind, and they kind of follow the same trend, but life gets a little bit more interesting sometimes just because it's chemistry and that's how it works. All right, so non-bonding atomic radius is nucleus to the valence electrons. Bonding atomic radius is between the two nucleuses divided by 2. All right. So these graphs here are really interesting. All right, and it does a really good job of showing the trend here. So it's measuring the atomic radius, and the farther it sticks out of the page here, the bigger the radius is. All right, so notice that if we start on a row, so let's compare this row with sodium, magnesium, aluminum, all those guys here. Notice that sodium is 1.66 is the atomic radius, all right, and then magnesium was 1.41. It goes down, okay, and then as we go to the right here, aluminum is even smaller, so on and so forth, so on. So let's think about why that might be. Atomic radius is decreasing as we're going to the right. Well, we know that the Z effective is increasing as we go to the right, and the Z effective is how much the proton is able to pull on those outermost electrons. So if the proton is pulling on those outermost electrons harder as we go to the right, that means it's able to pull them in closer. Okay, and because it's being pulled in closer, that means that radius is getting smaller. So that's why atomic radius gets smaller as we move across the period. All right. Now, so that explains that direction. Atomic radius trends opposite of Z effective along a period. But then, as we go top to bottom, notice what's happening with our graph here. We see that as we go from the top of the periodic table down to the bottom, the atomic radius is actually increasing. And that's following the same trend as the Z effective, right? So Z effective, remember, it's not as strong of a difference as we're going down. So that means there's something else that's trumping the atomic radius size. And in this case, that happens to be the fact that each time we go down, we're going up an n value, right? From here, remember this top row is n equals 1, this is n equals 2, and then n equals 3, etc. as we go down the periodic table. So as we add an n value, we're jumping up an energy level. And remember, every time we jump up an energy level, that is equivalent to an increase in radius. Okay, so as we move up, our radius goes out. All right, so because even though our Z effective is increasing ever so slightly, it's not enough to counteract the fact that we're actually adding on a new subshell. All right, so here's an interesting idea. Like, so when I was in like 5th grade, we had like pioneer types come in to our classroom. We did lots of things, and one of the things that we did was make candles. And we made candles by just taking a piece of string and a bowl of hot wax and dipping the string in there and pulling it out, and then waiting for it to cool down. And then we could take it to a different color of wax and dump it in the wax and pull it out. And like every time you did that, you'd end up with a little bit more wax on your candle. Okay, and so you create these layers. So essentially, so stick that in your head right now. As you go down energy levels, essentially what you're doing is just dipping your candle into the wax and adding an extra layer onto it. All right, let's see. So let's add this guy to our graph, and let's just change colors just for funsies here. Let's do dark blue. All right, so we know that atomic radius, okay, atomic radius here, from right to left increases as we go this way. All right, so that's our atomic radius. But we also know atomic radius increases as we go this way. All right, so these arrows that we've drawn here represent increasing whatever it is we've labeled it as. In this case, it's atomic radius. So notice that I drew atomic radius and Z effective on the same side for up and down because they are increasing in the same direction. But for the periods, they're flipped. Okay, just to help you picture it while you're working on textbook problems and so on and so forth. All right, now we've got sizes of ions. Now these are super interesting. Okay, Ions, remember, are what happens when we lose or gain electrons. So remember the candle analogy. We're thinking about the candles. Becoming an ion is essentially two different things. All right, it's either losing a layer, so taking a knife and shaving off those layers, or adding additional layers to it. All right. So it depends upon three different things, all right, our ionic size here, or the size of our ions. It depends on either the nuclear charge of whatever element we're talking about. That's still important, just like it was before for regular atomic radius. The number of electrons that are involved, okay, and then the orbitals in which the electrons reside, all right. So where are these orbitals? Are they in S, P, D, or F? Okay, now there's two specific rules that'll allow you to predict the size of ions very easily. Okay, anytime you're forming a cation, they always get smaller than they were before. All right, so lithium forms a cation, right? It becomes a lithium ion, and notice it gets smaller from a 1.28 size atom to a 0.90 ion. Okay, so that's easy. And this happens because we're essentially removing that outermost layer of electrons, but we're not changing the number of protons. So the things that were shielding electrons are now, the things that were shielding electrons are now valence electrons. Okay, so that's our cations. And then anions are always larger than their parent atoms. Okay, and so think of it as, so remember, anions are guys that get electrons added to them. Okay, and then as electrons get added to the outside of the electrons, or the outside of your electronic cloud here, we're adding electrons, and so we're getting farther and farther out, but our atomic number is not increasing, so our Z effective remains exactly the same. So this guy is just going to keep expanding. So those are your two important rules. So anytime you have a cation, the cation is always smaller than the parent atom, and anytime you have an anion, it's always larger. Okay. One more note about the size of ions. Okay, we get these things called isoelectronic series. Now, this word is really big. Let's break it down. Okay, so this term iso, okay, so like if you've ever heard the term like isobaric, probably not, isobaric or isothermal, okay, or let's see, isotrope, isotrope, okay, sorry, not trope, tope, isotope, there we go, isotope. No, so they all have this prefix iso. Let's think about what these words mean. Isobaric, well, this means same pressure, okay, same pressure, all right. Isothermal means same temperature, and isotope means same element, but it's got a different number of neutrons, right, isotope, okay. So really, this iso term means same, all right? So really, this means same electronic series. So these are guys, the electronic series, these are guys that have the same number of electrons, or they have the same electron configuration. Those are isoelectronic series. Okay, so they've got the same number of electrons or the same electron configuration. Okay, so when you're comparing things that have the same number of electrons or the same electron configuration, you have to think about their effective nuclear charge. You have to think about that Z effective. So as your Z effective is bigger, okay, your ionic size is going to decrease, right? That's like using a smaller magnet in the inside of your atom, so therefore it's able to pull those electrons harder. Okay, so if you look at these guys here, so all of these here, these have 10 electrons. Okay, this is the oxygen or oxide, fluoride, sodium ion, magnesium ion, and aluminum ion all have 10 electrons within them. They're isoelectronic. And notice that oxygen has 8 protons, 9 protons, 11, 12, 13, and as we go increasing the number of protons, our Z effective is increasing, right? Our nuclear charge is increasing, and then the atomic radius decreases, or the ionic radius decreases as we go this way. All right, so that's the isoelectronic series. So when you're looking at ions that all have the same number of electrons, you have to think about their effective nuclear charge, right? Isoelectronic series. Now we've got ionization energy. Okay, ionization energy is defined as the minimum energy required to remove an electron from the ground state. Okay, so you're thinking about, all right, how much does it take to remove an electron from that ground state? Now, specifically, when we take that as a measurement, it always has to be in the gaseous form, okay? Never solid or liquid or plasma, heaven forbid, all right? So it's always in the gaseous form of the atom or ion that you're specifically looking at, all right? And that's just, that's like the baseline. That's just what there's no specific reason for that other than that's what we've decided as a society. We live in a society, right? And so that's what we've kind of decided, is that we need, or that when we find values for the ionization energy, it's always going to be from the gaseous form of that ion. Okay, so there's several different ones you need to pay attention to. Okay, first ionization energy is the energy required to remove the first electron. Second ionization energy is the energy required to remove the second. Okay, third ionization would be the one to remove the third, etc., etc. Okay, generally, the higher the ionization, or the higher the ionization energy, the more difficult it is to remove the electron. All right, so if you're, because you're thinking about, well, how many joules do I need in order to remove that electron? The more joules it takes, the harder it is to remove the electron. Okay. So generally, it requires more energy to remove each successive electron. Okay. And then once you have all the valence removed, and you're like the noble gas, it's an order of magnitude harder to remove that next electron. Okay. So let's look at this. This guy here. So if we've got sodium, all right, so in this first column here, we've got the first ionization energies, and then in this column, we've got the second, and then third, fourth, fifth, etc., etc., all right? So if we're looking at these, we can kind of identify exactly what's going on here. So sodium's first ionization energy is 496 kilojoules per mole. Okay, so that's how much energy it takes to remove the first electron from sodium. If we remove the first electron from sodium, then it is out of valence electrons. It's, right? So, because sodium before, it's a 1s1 electron, or not 3s1, right? So 3s1 electron. So we've removed that electron. It's no longer there anymore. So now it's got core electrons, and it's got the same electronic configuration as neon. It's isoelectronic with neon. So if you try to remove the next electron from it, notice that it takes 4,562 kilojoules per mole versus the 496 kilojoules per mole. So it's a vast difference between the two. All right, magnesium. Now let's think about where magnesium is on the periodic table. Magnesium is at 3s2. Okay, so when we remove that first electron from magnesium, well, it takes 738 kilojoules per mole to remove that first electron. So then it turns into a 3s1. Okay, and then it takes 1,451 kilojoules per mole, and then all the 3s is gone, and now it's isoelectronic with neon, which is the nearest noble gas. And all of a sudden, if you want to remove that guy from neon, it's going to take 7,733. Okay, and then we can kind of keep going just like that. All right, notice how they don't even bother writing in the values for here, because these get like astronomically huge as you go to the right here. Okay. All right. So periodic trends, ionization energy, and these are going to be based off the first ionization energy. That's the one we kind of use to predict, because once you get past the first ionization energy, the second and third kind of jigger-jag around depending on where it is on the periodic table and so on and so forth. All right. So generally, first ionization energy increases as we go across a period and decreases as we go down a group. Okay. The S and P block elements show a larger range for ionization energy. Okay, so as we look at the D and F, so here we go. So we've got these guys here. Okay, so notice the big difference in the S and the P. That's what, or the two S values. It jumps from 520 to 900. Okay, versus the transition metals is 63, 659, 651. It kind of doesn't really change as much. But then if you once you jump over the P values here, it changes quite a bit. All right, let me make sure. Now there's a couple of things that I want to point out while we're at this slide here. Okay, notice how when we jump from this column here, the end of the first D, so we're 3D10, right, to this guy here, we're going from a full subshell. Okay, so this would be a 3D10. That means that we've got the whole that D block is filled, right, for zinc. And so that whole, because it's all filled, it's pretty stable, and it takes quite a bit of energy to remove that first to convince it to be a 3D9. Okay, but then if we compare it to gallium right here that's right next door, it's going to be a 4p1, right? Okay, and so it takes less energy because there's only one electron on that sublevel. It takes a little less energy to remove it than it did for the subsequent first ionization energy of zinc. Okay, so look how the ionization energy generally increases as we go to the right, but this is one notable exception that you should be aware of. Another one you should be aware of is the difference between nitrogen's column here and oxygen column here. Okay, so if we look at nitrogen, nitrogen is at 2p3. Yeah, 2p3. Okay, so if we were going to draw out nitrogen's orbital box diagram like so, it would look something like this, right? You'd have the 3 box like that. Now, if you wanted to remove one of these, like we already know because when we talked about the exception that chromium has in its electron configuration, that a half-filled orbital is actually pretty dang stable. This is, comparatively, this is a happy place to be. Now, is it perfect? No, it's not quite like a noble gas, but it's pretty happy. So if you want to remove this, then you're going to have to provide a little bit more energy. Now, if you look at oxygen right next door to it, oxygen is 2p4. Okay, if we were going to draw its orbital box diagram, it would look something like this. We'd have the arrows 1, 2, 3, and then we'd have a third arrow like that. Notice how it's half full plus 1. So while oxygen still really doesn't want to lose that electron that it's got, it'd much rather gain 2 more electrons to become like neon. It doesn't take nearly as much energy just to remove this first ionization or this first electron compared to what it does for neon. So those are the 2 big exceptions that I want you to notice about. When we're going from the last of the D block to the first of the P, there's almost always like a little jump there. And then as we go from halfway filled orbitals, this P block to the halfway, once we're at the halfway filled P block, there's almost always a jump down that's counter to the trends here. Okay, also notice that your ionization energy increases as you go up as well, and that's because you're getting closer to that nucleus. All right. So let's draw this out here. Where's my periodic table? All right. So we've got. Let's pick a new color. So ink color. How about? Oh, we already did red. That was silly. Let's do purple. All right. So our ionization energy, all right, IE, increases as we go this way, and then it also increases as we go this way. Now, I know I'm spending time to write this out, but I really don't think that you want to try to memorize this. This isn't the way to go about it. It's not going to be the most beneficial for you. You're going to be much more benefited if you take the time to think through all of these things and walk yourself through why do all of these trends occur. All right? We just talked about that. Okay, now this is kind of interesting. We just kind of talked about this in general, but this is a slide showing you what happens as you become anions or cations. Okay, as you become cations, you're going to lose electrons. So like this guy, lithium, was 1s2, 2s1, but when it becomes a lithium ion, it becomes 1s2. Right, the 2s1 is gone. And anions do the opposite. You're adding electrons to it. Okay. Finally, we've got electron affinity, and this is the energy change that's accompanying the addition of an electron, okay, to a gaseous atom. Where's my, oh, there it is. All right, purple's really hard to see where the pen is, huh? Let's go back to like red. Okay, so anyway, so electron affinity is defined as the energy change. So in general, so essentially what you're saying is that the atom has, it's like, ooh, I'd like to get that electron, but it has to buy that electron. So in order to buy it, it has to pay it with energy. Okay. And that's typically what we're thinking here is that, so like, for example, chlorine here is going to gain an electron to become the chloride anion. Well, chlorine is going to be like, well, I'd much rather have that electron than this energy that I have. So it's going to be willing to pay this energy. Now, because it's paying the energy, it's going to be it's defined as an exothermic value. all right, because it's paying that energy. It's exothermic. So for most elements, it's negative because they're paying electrons, all right, or they're paying energy to buy electrons. All right, general trend in electronegativity. As you're changing in a group, there's really not much change. There's absolutely there's no trends. Like, for example, this first column here, the alkali metals, the trend is that the electron affinity increases as you go down a group. However, for the very next, the alkaline earth metals, they do the opposite. As you go down the group, they become more negative, right? Anyway, so you can see there's not much of a trend as you go down a group. Across a period, it generally increases. It follows the same trend as ionization energy, except for a couple of exceptions. And you'll notice that these exceptions are almost exactly like the exceptions that we talked about in ionization energies. Okay, first of all, when your group 2A, okay, when your S sublevel is full, then then the electron affinity stops increasing there because it doesn't really want to gain another one. It's got a full S level. All right, and then in the group 5A, so this is halfway through, so this is nitrogen, phosphorus, all those guys. Okay, when that guy's halfway full, it does not want to get another electron, and then therefore the electron affinity is rather low right there. Okay, so notice how, you know, silicon here is at negative 134, phosphorus is at negative 72, and now all of a sudden we jump up to back to negative 200 again. Okay. Yep. Okay. And that's where we're going to stop for now. Oh, we should add that to our column here. Electron affinity. So electron affinity has the same trend as atomic radius. Okay. Electron affinity, atomic radius. Oh my goodness, drawing to the left is really difficult on this thing. Anyway, so that's it for the first half of Chapter 7. Do your textbook problems. Let me know if you have any questions, and I'll see you on the flip side.